Alright, we're recording. What is up, YouTube? We're here with another tutorial. This one is event queues and finite state machines, and then at the end of this tutorial we're going to be going over how our last car's lights worked. And I'm going to kind of provide you with a block diagram of like how the code actually worked, and then we're going to jump into it, looking at the actual code. And this is where this tutorial, I'm hoping that it's like one of the last tutorials that I'm going to run, because this is where you kind of see all of our where all of our libraries kind of come together and play, and how they operate and things of that sort. So after this tutorial, I hope that you guys have enough resources to kind of get started with your own projects and kind of get started with drawing the block diagrams and then implementing every single part and then testing that every single part, and then moving further and kind of bringing your modules together and testing them together, and then kind of coming to me and like in the entire process, I will be going through code reviews with you as well. So let's jump into it. So these are the topics that we're going to cover. Finite state machines, what they are and how they work, and then we're going to do a demo where we're going to blink a light using a finite state machine. Here I'm just going to use printf statements so that you guys can see kind of like in console what's going to happen. But if you built the same project on an STM32, you will see the light actually blinking. But in the past tutorials, we've made STMs blink like 1,000 times, so I didn't see the need for it. And then we're going to talk about event queues, which is a really important thing. Pretty much all of our projects use this, and they're kind of the glue that bring all of your modules together. It's basically how your entire modules talk to each other. So we're going to see how those work as well. So finite state machines. So I just searched up Wikipedia what it says. It's a mathematical model for computation, and it's correct. It's a mathematical model. It's kind of like it's an abstract concept. So what it does, or what I've found out from experience, is that it helps a lot with the control flow of your application. Instead of having a giant while loop where you're having like a lot of if statements and go-to statements and all those kinds of stuff, you can just put the entire logic of your application, break it down in terms of states and what needs to happen in every single state, and that'll help you understand your project much easier. It becomes easier to code and easier to understand and easier to debug as well. So and you absolutely need to know what finite state machines are if you want to contribute to the team, because even some of our libraries have internal state machines themselves. So that's how they work themselves. So you won't be able to use those libraries. For example, our CAN library uses a finite state machine to send and receive messages. So very important. Definitely keep it in mind. So your program has so this is how you make a finite state machine. Your program usually has a finite number of states, and it can only be in one state at a time. And then upon entering a state, you can take actions. So what is an action? It's basically what happens when you enter that state. So here's an example for like making the car's signals. So I'm just going to zoom into here. So let's say we want to make a state machine for like a car's signals. So you can have a none state, and then you can go to signal left, come back here, signal right, come back here. You can go to hazard. So signal left is, for example, when the control stalk is pulled low, and you know that's how you get into the signal left state. And most cars usually have a stalk. It's not like a button. So you pull that thingy low, and then it'll go left, and then you pull it high, and it goes right. So that's basically usually like on the left side of your steering wheel. Let me actually Google steering stalk. So let's see. Yeah, there you go. So this is how a steering stalk looks like. Oh my god. I just want to take a look at the image. Open image and then the tab. Hopefully this will do it. Okay, there we go. So this is the signal stalk usually. If you pull this low, that means signal left, and if you pull it high, it means signal right. And then there's also the hazard button, where usually it's like somewhere in the middle of the car, like in the center console or something, where you press it and both your signal lights blink. So, all right, good thing I Googled this. So you want to basically have this state machine to do all those state transitions. So this actually doesn't work, and we'll see why. So these are all the input events that your board will get. Let's say you are writing code for the lights board. So all of your input events are basically steering stuck, left on, left off, right on, right off, and then hazard press and hazard release. And these are pretty much all the states that you have, right? So let's just try and kind of do some state transitions. So from state none, if you go to left stock on, you go to signal left stuck, right? And then if signal left stock off event comes in, you come back to none. So this part makes sense, right? So no one has any problems with that. Same with hazard, you can go there and come back. Signal right, you can go there and come back, right? But there's one problem, and we're gonna see what that happens. So from signal left, if the user presses the hazard lights, well, the behavior of a car is that both signal lights will start blinking together, right? So from here you go to hazard state, right? And same with signal right. If the user presses the hazard light, then it will go to hazard, right? But the problem arises when you actually want to get back from the hazard state. So let's say the hazard gets released. So do you go from hazard back to signal left, or back to none, or back to signal right? So remember when you are, for example, previously in signal left, the stock is actually pulled down, right? And it's actually still in that state. So if you go from signal left to hazard, and then if you turn off hazard, you actually have to go back to signal left. And then same with signal right. If you've been previously in signal right, then you have to go back to signal right again, right? And then same with none. So if you previously were here, and signal left or right was not pressed, then you have to go back to hazard, to none from hazard, right? So this means that when you enter the hazard state, you kind of have to know what was the previous state that you were in, and then go back to that previous state, right? Well, that's kind of like a bad solution to keep the previous state in a variable, because it kind of takes away the point of a state machine. The whole point of state machine is to have, like, at every single state, just transition to other states. If you bring too many conditions in, then your state machine becomes hard to understand. So one easier way to get around this is to add 2 more states. So you can go from none to signal left, and then if someone presses hazard, you go to signal left hazard pressed, right? So when you're here, it means that both the lever is low and the hazard light is pressed, right? So if you turn off signal left, then you can just simply go to hazard, right? And then if you turn it on again, you can go back to here, right? Notice that in these 3 states, both signal lights will blink. However, the value that these 2 extra states add is that they actually keep that information with regards to what the state of your signal stock is, right? So this is kind of like the state machine that takes care of all of those. So we kind of started with a simple design, but then we realized that this doesn't work, so we went here, right? So let's get to the next concept, which is events. So events are the input to our FSMs. So why am I saying our? Because this tutorial is mainly a tutorial for kind of finite state machines in general, but more specifically how our finite state machines work. We actually have our own library for finite state machines, and we're going to jump into that and see how that works. And our finite state machines take events as inputs, and they're usually what begins the transitions, right? So state transitions usually begin by the inputs to our finite state machines. So not only finite state machines use events, you can write other modules that take events as inputs as well, right? So events are not specific to state machines. Other modules will take them in as an input as well, and this is actually really important. Almost all of your modules will have to do something with events, and you will shortly see why. By module here, I mean basically a basic C file. So for example, when you have like in the C programming tutorial, I basically said what object orientation in C means, and here when I say module, I basically mean the same thing. So a module is basically a module or an object in C. So go back to the C programming tutorial if this module is not familiar, the term module is not familiar to you. So we're going to do a demo, blinking LEDs. I actually gave this as an assignment to a lot of you guys. So we're going to make some LEDs blink. So let's see, this is a simple state machine that I've drawn here. So we can have on state, and then delay state, and then off state. So you can go to on, so from delay, upon an LED on event, you can go to on, and then from on, upon a delay event, you go to delay, and then from delay, upon an LED off event, you go off, and then you go back to delay, right? Notice that I could have done this in like 1,000 different ways. I could have had a delay and then a toggle, and then come back to delay, so on and off. Instead of that, I could have just had toggle. Or I could have had an on event and an off event, and then within the on event, I could impose a delay, like in its output function, I could have done that. So there are multiple ways of doing this. I'm just sticking to this because it's just, I thought that it would be a simple way of showing how finite state machines work. So first we need to define our events. So our events are LED on, LED off, and delay, right? So notice that there's not always a one-to-one mapping between your events and states, right? So let's go here. So here you have, for example, signal left hazard, so for example, you have the signal left event, state, right? But for the signal left state, there are two events, right? So you have signal left stock on, and then there's off, right? So there's not always a one-to-one mapping between your states and your events. So they're two separate things. So in this case, because our finite state machine is really simple, our states are also on, off, and delay. So it's just how it is. So let's go and show you what the code looks like. Let's make this a little bit bigger. Firmware MSXII. Yeah, it's just, I don't know what's going on with it. Yeah, no, it's okay. Sometimes if I have too many applications open, the fans go off. So controller board, blinking LED state machine. This is the project that I have. And by the way, if you want to follow along later on, the branch that I'm at is Soft 22 Peripheral Tutorial, and the project is Firmware MSXII. I'm going to also put this information in the description of the video as well. And I've become a YouTuber. Blinking. Really? Hopefully, if the YouTube videos get enough views, that could be another source of funding for a race. So this is what the project is. So notice that I've just defined an enum that contains events on, off, and then delay. And then usually we finish all of our enums with num and then whatever that enum is. So in this case, I just put num events. This will have multiple benefits. One good thing that it has is that because this starts from 0, and then this becomes 1, this becomes 2, this becomes 3, which happens to be the same number as the different events that we have. So it's a really good way to kind of show that. There's also, when you're defining your arrays, you can actually use a really nice notation that I'm going to show you soon, where you can use these as the indexes, and it'll be really nice when you especially want to index into an array. You won't have any magic numbers. You can just use these enums. So that's so how our finite state machines work. So usually, whenever you want to take a look at the how our libraries work, take a look at the test file. And I've already done this in one of the past tutorials, so I'm not going to go over it again. I'm just going to explain how this code works. FSM blinking LED state machine. So over here, this is the GPIO address for that LED that I want to turn on and off. And then here's our event definition. And then we've defined our own macros for declaring a state machine, and those macros kind of make it easier for you to kind of, like, when you take a look at the code, it's kind of like a cool syntax where you can define a state machine. You can obviously jump into the definition of these macros, and they all go all crazy very quickly. So for example, every time that you declare a state, that basically defines a static variable for you, right? And then it does FSM state transition. What is this? This defines a transition function for that state, right? And then FSM add transition adds a guarded transition with state true, blah blah blah. So these are all, like, if you want to jump to the definitions, they'll help you understand how the internals of our state machine works, but you certainly don't need to understand how all of this works to be able to use our state machines. So you should be able to just use our state machines as a library. So don't worry about how it's actually made, because that is not necessary. So we declare our states, right? So every single one of these will declare a state variable. And then you declare state transition. So from state on, when the event's delay comes in, we go to state delay, right? So if you take a look at this, so on upon the delay event, we go to delay states, right? And then same here, on off, we go to state delay. So on off, when delay comes in, we go to delay. And then from delay, we can actually go to two places. If the event is on, we go to state on. If the event is off, we go to state off. So we're at delay, LED on takes us here. LED off takes us here, right? And then we have the output functions of every single event. So what is an output function? It's the function that runs when you enter that event, right? So state on output here, I've defined it as static void this, and this is what the function signature for that event looks like. So you have to do it this way. And then this function gets called every time you enter that state. So you can see that I've done GPIO set state, and I'm setting the state of that address to high. So because I'm not going to run this on a controller board right now, I just print it to the screen, setting LED state to on. So same goes for the off state, and then same goes for the delay state, right? So in the delay state, I just call this delay function for 500 milliseconds. And then here we are initializing our state machine. So FSM state init state on. So it means that so here is where you actually link your state output functions to the states themselves, right? So when you do state init, it takes the state as an input and the output function for that state as an input. Obviously, you can use the same output function for multiple states as well. So if you want the same thing to happen in those states. Yeah, so that's how you initialize your states. And then you need to initialize the actual finite state machine itself. And then so that's how that works. How that works is that you define a static variable, static FSM SFSM. The reason you define it as static is because you want this to persist throughout your application. So either you use this directly, or you will have some other high-level struct that one of its fields is a finite state machine, and that will be static. In general, you just want to make sure that your variables persist throughout your application, especially fundamental variables such as your finite state machine, because this is the object that you want to persist. And then you initialize the state machine. So you pass in the pointer to that variable, and then you can give it a name. This name is mainly for debugging. And then the initial state that you want it to be in. So initially we're in state off. And then last but not least, you just pass in a context. So this is basically the context object. So I'm just going to jump to the definition. You can see it here. Void star context. All right? It doesn't show? Okay, let me just go back. Okay, now it's updated. So here I'm just passing the state machine itself as the context, but you don't really have to. You can just pass this as null. And what happens is that this context variable will be null in that case. But in none of these output functions, I'm actually using the context variable, right? And if you don't know what context variables mean, just take a look at our previous C programming tutorial, because over there I explain what context is. So I initialize interrupts, soft timers, GPIO, and I initialize the GPIO pin, and I initialize the finite state machine. And then I will have an array of events that I'm going to loop through and constantly pass these events into my state machine. If you remember, I said that the input to our state machines are events. So let me explain one subtlety here. So here I've defined an enum and I've named it blink event, right? What this is that it's basically just an event ID, right? However, we have our own, so this really this should be a blink event ID because it's not an event itself. We have another event object or a type def for event, which is stored at the event queue.h, right? So every event has an ID and has some data. So this is pretty important. And we will see how our event queues work shortly. And it'll make sense once we get there. But basically, every time that you want to pass in an event to our state machines, you would have to create one of these objects and then set its ID to that ID that you want. And then if it needs some data, you can basically pass in that data as well. And in your output functions, you can actually have access to that event as well. So if you want to do something with the data of that event, you can actually take a look at it by, for example, doing something like data, right? This will actually have the data of that event that you passed into your state machine. So we loop through this array, and then we pass in the event. So we create an event object, and then we pass it into our finite state machine. And the way that works is that we just call FSM process event with the state machine, and then this event. So we pass the pointers in. And that's how, so this pretty much comes back from object orientation. We never pass in the actual object itself. We always pass the pointer in. Yeah, so that's how the code works. I think I've covered all the major parts about it. So this is how you run it. So make run project blinking LED state machine, and then you pass in platform equals x86. So this is how you run our projects in Linux. So right now I'm in the VirtualBox, Midnight Sun's VirtualBox image. So let's just run it. So now you can see that it says on, off, on, off, on, off. And if I actually run it on a controller board, you will see that it blinks. All right, good. So that's how our demo worked, or like that's how you can blink LEDs using a state machine. So this is a very simplistic example. We use state machines a lot in our car, especially when we want to handle, for example, the sequencing that happens when we power on the car, when we power off the car, and all that stuff. And it's super, super important. And I'm gonna show you, like at the end of this tutorial, I will show you the lights, so you will, it'll make sense. So event queues. What are event queues? Your program by default does a lot of things, and that includes listening on the canvas for some messages or possibly sending some messages, and then reading from sensors and then closing and opening the relays. For example, in the case of battery management, you would have to constantly look at the sensors of the battery pack and see if it's over voltage, under voltage, over temperature, under temperature. All that stuff you need to protect against. And so you need to read and then close the relays. Sometimes some other board tells you something to do, and then based on that you need to open close some switches. So all of these stuff has to happen within your program, and because it's an embedded program, you will always have that kind of like while true statement in your main file, so that it never exits, right? But it becomes very hard to manage your program if you want to do it all in just like one while true file. So the way we handle it is basically is using the event key. So manage all these activities, you need to break your code down into modules. But yes, okay, so we break it down into modules, but what does every single module do, or like how do they interact? That's kind of like a really, this is a really high level statement. How do you actually implement it? So how these modules interact is handled by events. So one module raises an event, and then the next module takes that event as an input and acts upon it. Usually your modules don't directly call each other's functions. Sometimes they might. We will see an example, but usually you want to keep them separate, because if a module directly calls another module's functions, that means that there's a dependency between those modules. So your code becomes coupled in that sense. And when you have coupled code, it's usually harder to change it. So if this doesn't make sense, just keep it in the back of your mind and constantly try and think about it, because it's a very high level thing that I kind of just learned over kind of a couple years that I've been coding. So all of the events need to be coming from one place, and that place is the event queue. So as its name suggests, it's basically a form of storage, kind of like a queue or a stack. It's a singleton, so in our entire application, we will have only one event queue, right? You cannot have multiple because event-based programming implies that you only act on events. So this is basically the part that tells you what am I to do next. And it's also a priority-based queue. So you can actually raise events with different priorities. If you just take a look at our event queue.h file, you can see that there's another method, raise events priority. So events that have higher priorities will be popped first. So that's basically what it is. So this queue is actually not like a FIFO queue or like a LIFO queue. It's basically a sorted queue based on the priority. So each module that you develop either consumes events or it raises events, or it does both. So how does it consume events? It's usually that like how is this handled? Usually that module defines a function called, it's usually that module name and then process events. And if you take a look at it, look at our, for example, state machine, that's basically what the function looks like. And if you take a look at the old cars code for a lot of the projects, this is kind of like the naming convention that they follow. And your code can follow kind of the same naming convention because it'll look consistent. It's easier to understand other projects once you understand these kind of rules. And then each module can raise events, and the way you raise an event is basically by calling events raise. So calling event raise is basically you pushing to that event queue, a new event. Or it does both. So while you're processing an event, you realize that you need to raise an event for another module to take action. So you can just raise a new event, and then that module will receive that event. And we'll see how modules receive events, because right now we just talked about how they raise one. And well, here we set that when they implement this function, but where is this function getting called? We'll see that. So to kind of bring all of these together, it's good to talk about one of the old cars projects. So MS-12's lights, I wrote the code for it. It's by default the one that I kind of understand the most. However, if you look at the rest of the car's code, it will be following the same pattern, more or less. So this will help you guys understand it much faster. So when I was first given the project, I didn't really know anything about finite state machines or event queues or anything. So it pretty much, like, the specifications that I had for the project were like pretty high level. So it receives CAN messages, and the CAN messages talk, like, pretty much tell something to do. That was Siri in my phone. So it receives CAN messages. So a message tells you, for example, to turn on a light, or turn it off, or for example, blink the signal lights or something like that. And then yeah, so that's pretty much what that board does. There's also an extra functionality where because there was two lights boards on the car, the rear lights board would send a sync message to the front right lights board, in which case they would kind of restart their counters because the clocks on these boards are not exactly the same. If you turn on, for example, the signal lights, the front and the back lights would go out of sync. So they would not, like, after enough blinking, they would kind of go out of sync. So that was kind of like an extra added functionality that I didn't really put here because it wasn't that necessary to what it actually did. All right, so let's go to the next one. So this is the kind of block diagram that I want you guys to kind of come up with. So every single one of these blocks actually maps to an exact C file and a .h file in your actual project, and it's super, super important that you guys come up with this first, then start writing your projects. And it becomes really easy because once you understand the entire project, how it works from a high level, implementing it will become super, super fast. So usually you want to think about it in this sense, and you don't begin by just writing code first. So over here, I'm just going to go over every single module and explain it very quickly. So lights CAN is a module that just has listens on the CAN bus and just receives a CAN message, and then as a result of that message, it will raise an event that is specific to car's lights. And then by raising that event goes to our event queue. And then main will pick it, and then it will pass it to different modules. So what light strobe does is that it blinks the strobe light. Light signal FSM is basically a finite state machine that contains the light's states. So it's the exact implementation that I provided here. Sorry, actually no. This one, right? It's this one. So, okay. And then Lights GPIO is a module that takes in an event and then turns on or turns off a GPIO line. This is how we kind of like turn on or turn off the lights. And then this blinker module is a module that actually makes stuff blink. So when it implements two different methods. One is blinker activate and one is blinker deactivate. So once you activate the blinker with a specific kind of peripheral, it will repeatedly raise events. For example, like if I have light signal, it will be light signal on, and then it will raise a light signal off, and then it will raise a light signal on, and then it will raise a light signal off. So it constantly just raises events, right? So I'm going to walk you guys through one example where a signal message comes in, and then how this light as a whole turns the signal lights on, right? So let's say a CAN message comes in and is for the left signal. So signal left on, lights CAN module basically receives that event and then receives that message and then raises an event. And that event, we're just going to name it signal left on. So our event queue right now has that signal left on event in it, right? And then main will pop that event. So main now has that, and our event queue is empty. And then it passes it into the to the rest of the modules, right? So every single module takes a look at that event. If that event is for that module, it will process it. If it's not for that module, then it will not process it. It'll just ignore it, right? So right now, this signal left on is an event that is supposed to be processed by light signal FSM. So strobe and GPIO will ignore it. So let's go down. So finite state machine, like light signal FSM, will pick it up, and it transitions to the left state. So over here inside, it's like a state machine. So that state machine will do its job, and then it activates the blinker, right? So once this blinker gets activated, it will repeatedly raise events. So it will repeatedly raise left signal GPIO on or left signal GPIO off events, right? So when it raises those events, what happens? For example, let's say right now we are in a state where all of the car's lights are off. So this guy raises an left signal GPIO event. The event queue will get that, right? What happens is main pops that and then passes it again here, right? So this time, the lights signal GPIO on is actually to be processed by light GPIO, right? So light signal FSM, like the events that I passed into light signal FSM previously was a different event than this one, right? And then lights GPIO will now turn on the left signal. So it'll call GPIO set states on the corresponding GPIO address with the corresponding state, right? And then blinker will, like after maybe like 500 milliseconds, the blinker will raise another event, and that event goes here, and it'll turn it off again. And it'll go back and then turn it on again. It'll go back and turn it off again, right? Notice that if we had a simple light, for example, like headlights, the message would come in, event would get raised, and it would just directly go to lights GPIO, and then lights GPIO would turn the headlights on. Because you don't have any blinking functionality, it's pretty simple how that works, right? But for things like strobe lights and signal FSM, they all use blinkers themselves, right? So how do you turn the blinker off? Well, a CAN message comes in for example, left signal off, right? That'll go to event queue, main would pass it here, and then this guy would transition into the, for example, non-state again. And then once it transitions to non-state, it'll deactivate the blinker, right? So that's how you stop blinking. So that's pretty much how that works. So now let's jump to the actual source code and see how it's done. So over here, I'm in the Firmware XIV project. But if I go back to firmware, the firmware project, this is where the source code for the old car is. Lights control is the name of that project. So if you want to follow along, be sure to come here. Let me make this a little bit bigger. So this is what the main file for that lights control works. As you can see, I have like light signal FSM, and then some CAN storage, some strobe. So my strobe module is fairly simple. We will go and see how that works. And then because we had, so just ignore this board type address, but very quickly, if I wanted to explain that, our lights boards looked exactly the same, and the hardware was exactly the same. So that basically required software to adjust whether it's the front lights or the rear lights, and I would read it from like a GPIO pin. And that's basically all this is for. So I set up CAN. That's how I receive CAN messages, and then I initialize all of my modules, so GPIO init, interrupt init, and all that kinds of stuff. And then this is where I get whether I'm the front board or the rear board. So over here, I initialize all the modules that I had. So I load the configuration. So whether you're front or back, you might have to turn on different lights. So I just load the configuration, and then I initialize every single module that I have. One extra thing that I'm doing is that I'm just like taking the status, and I'm failing early, and I'm logging it. So this is good practice if you do it. So I initialize lights GPIO. I initialize lights CAN. So these exactly map to these stuff. So lights GPIO gets initialized, and then lights CAN gets initialized, and then lights signal FSM. So this guy gets initialized, and then lights strobe gets initialized, right? There we go. And then this is all my program does. It constantly, so this is basically what it is. So this event process is basically a function from our event queue module. This is what actually pops the next event. So this function will return a status code of OK if the event queue has some event in it, and it will return status code empty if it doesn't have an event in it, right? So if we go back here, this main will constantly take a look at the event queue and see if it has a new event, and it will pass it in, right? So if the event queue doesn't have an event, then main just constantly just pulls for it, right? So that's how that is done. To be able to grab this event, you would have to declare an event object, right? And this is our notation for just setting a struct to 0. So after we grab the event, we pass it into all of these different guys, right? So CAN process event. This is for our CAN library. So like I said, our CAN library has an event. A finite state machine itself, and that finite state machine takes an event as an input. We also use this in our CAN tutorial, so take a look at that video if you're unsure what this does. So we first pass it to the CAN process event, and then after that we just constantly pass it to the rest of our modules, right? Lights GPIO, light signal, light strobe, right? So taking a look at light signal, it pretty much does all the state transitions, and then I have some signal left, signal right. I have all the transitions here. These are basically the implementation for this diagram that I drew here. So it looks exactly like that if you guys later want to go and take a look at it. And then let's take a look at the blinker module, blinker.h. So it's called lights blinker here. So as you can see, I've defined some storage because to use a blinker, it will use a timer. So I have all the variables that I want to play around with. I will keep them here, right? And then same thing with the object orientation in C. So I'm passing the blinker star to every single one of my functions. So you can see that you first have to initialize a blinker, and then you activate it or you deactivate it, forget about this force on. This is for syncing purposes. So if you read the comments, it'll pretty much explain what that does. So lights blinker, activate and deactivate pretty much do all the magic work for blinking a light. So what does this guy do? So you call this guy, the screen hasn't updated. Okay, now so you call this guy with a lights events GPIO peripheral, right? So this is pretty important. That peripheral is defined over here, right? So you can see we have high beams, low beams, DRL breaks, and all that stuff. So I will look at that peripheral and I map it to some event, and then I will raise an event, right? So if the state was on, it'll raise an on. If the state was off, it'll raise a off, and all that kinds of stuff. And then I will start a soft timer, and that soft timer will call this timer callback. Okay, now the screen has updated. So yeah, you can see it here. If you take a look at this code, it's not that hard to understand. Within the callback, I do another callback, and I will just change the state. So if it was on, it will go to off. If it was off, it goes to on. And this guy doesn't call GPIO directly. It will raise an event, and then the GPIO module will deal with that, right? Lights GPIO. So let's take a look at this guy. This is the same thing. You initialize it, and then you have a process event function. Let's see what this process event does. It pretty much takes a look at that event, right? And then it figures out the state, whether it should be on or off, and then it calls this set outputs function. In this set outputs function, here we are using a bit set. So output bit set, if you take a look at it, it's basically a 16-bit integer. And then I find, like, each one bit corresponds to a specific peripheral. So I basically figure out the index of that bit set, and then I will take a look at this. So this outputs is probably a lookup table. So basically take a look at the this struct, and lights GPIO output has a GPIO address and GPIO polarity. What this is for is because some of our lights were active high, some were active low, so I just kept track of them by defining a new struct. And then I just call GPIO set state. So that's how this part works, right? And then, so I went through light scan, I went through this guy, went through this guy. Strobe is pretty much like signal FSM. It uses a blinker itself. So lights, strobe. So it has an init function and a process event function. So in the init function, it just calls lights blinker init. So it calls the blinkers init function. And then in the process event function, it activates it or it deactivates it. That's that. Yeah, so that's how lights works. So it's fairly simple. You pretty much break your program into multiple modules. It seems to the outside user as if all of these modules are running at the same time, whereas they don't. In an operating system, usually each one of these would be probably like a different thread, and then they would have like a shared resource, which would be like a mutex or something. This event queue is basically your shared resource in this case. Here we don't have any operating system to help us. So we define our own modules and we handle the event queue. And to a certain extent, this is actually pretty nice because we have full control over what to execute next. So if, for example, something goes wrong in the car, we need to like get in a faulty state and like disconnect the batteries, we can exactly do that because we can assign a very low priority event to that event that turns off the batteries or opens the relays, right? Same thing happens with our CAN protocol. We can assign a really low message ID to a message, and that message will take precedence over all the other messages, right? So that's our lights. So the source code, yeah, we jumped to the source code, we took a look at it. So what are your tasks now? So your projects need high-level design first. So this kind of design that I provided you with here, you need to do this yourself, right? To figure out what your project does. So for example, if your project is center console, you would have to have so it would be the reverse of this. You would get your inputs from GPIO, and then you would send a message. So you would have, for example, like a CAN module that would broadcast messages. So it would take an input as an event. So you would take an event as an input, and then it would send messages. And then on the other side, you would have another, for example, center console button module that would use interrupts to find the button presses, and then it would raise an event, right? So that's how your kind of program works. So in general, come up with designs. So your program has like multiple modules. Each module is usually independent. It doesn't usually directly use another module. In this case, the exception was light strobe and light signal FSM that directly called blinkers methods, right? And the event queue is the glue that kind of like brings everything together, right? Because in order to talk to each other, these guys will raise an event to the event queue, and then the event queue passes that event into the other module, right? So for the critical projects, I will design them and you will implement them. You're welcome to participate in the design, and when I kind of explain you the design, you will I will explain why I'm designing it a certain way so that you can learn. But by default, because we have deadlines and stuff, I cannot wait for everyone to just like come up with the design themselves because it's just slower that way. So I will come up with the design completely and make sure how your firmware works, and then I will just give it to you and you will start implementing it, right? And for the non-critical projects, well, obviously I'm going to do the critical projects first, so you're welcome to design it yourself. And if time allows, I will come and design your project, or you can just talk to me whenever you're designing the project yourself. All right, thank you so much. This was hopefully the last tutorial. If there's more tutorials, I will explain them. But right now, I think this should be enough for you guys to get started on your projects, and hopefully within the next 2 weeks, we will get the entire major parts of the car done. And the major parts are pretty much battery management system, front power distribution, rear power distribution, center console, pedal boards, and motor controller interface. So these are the major parts, because once we have all of them together, we can actually test our electrical system and actually drive the car with them. So pretty important stuff.